We have here assignment about standing waves. A hollow tube of length L, so it's hollow on both ends, open at both ends as shown at right, is held in midair. A tuning fork with frequency FO vibrates at one end of the tube and causes the air in the tube to vibrate at its fundamental frequency. So you could Google fundamental frequency, see what that is. Express your answer to parts A to C in terms of L and FO, so in terms of the length and frequency of the oscillator. Whatever oscillates, it have around the oscillator, it has the same frequency as the oscillator. So this air here is not very important for this assignment, but this air here or water or whatever will always have the frequency of the original oscillator. Okay. Now let us see, determine the wavelength of the sound. So we need to find the wavelength at these conditions, if we have the length of the pipe and if we have initial frequency. Determine the speed of sound in air inside the tube. Determine the next higher frequency at which this air column would resonate. Next one and so on. So next is some other, not fundamental frequency, but some other harmonic. And what is the next one? Well, you could search for it and find yourself. This is when the tube is open at both ends. This is when the tube is closed at one end. It's very similar, but in some case different. So let us see first solution to this assignment. Again, if you want to know more about these things, standing waves, sound, fundamental frequency, sound in the hollow tube, and so on. And here is something that you could find at hyperphysics. As you can see, if it is open at both ends, there is a frequency of the there is a half of the wavelength from here to here. It is if it's closed on one end, there is fourth actually of the wavelength, and so on. So this is just the way it is. Why is this half wavelength? Well, this is the one part of the wavelength. This is wavelength, half of the wavelength once of the one sound. So as you can see from here to here, and then that is a half wavelength. And now back again, and that will be a whole wavelength. So this is the half of that. So if you place a barrier here, you will get this. So as you can see here, open cylinder at air column. First of all, in the terms of the wavelength, length is actually half of the wavelength. And as you can see here, frequency of that thing here is when you divide speed of sound with two lengths. Actually, frequency of anything wavy is when you divide speed of the wave with its wavelength. And 2L is actually lambda. So with that in mind, L is lambda divided by half, so L is length, lambda is wavelength, and from here lambda is 2 times L. L is that, and always when you have some wave that's travel, when you have some waving, may that be a light or a wave on the pond or sound wave, you always have that speed of the wave is equal frequency times its wavelength. And we know that wavelength is actually 2 times L. So 2 times L. So the speed of this sound in this air column is 2 times FO times L. And this is the solution under B. And this is the solution under A. We already did this just by placing it here. So let us see, determine the wavelength of the sound. So this is the wavelength, 2 times the length of the open tube. That's it. Solution under B. We need to find the speed of sound inside the air. So speed of sound is frequency times wavelength, and that is that. And we need to express that solution in the term of L and FO. So let us see. Okay, that is L, and here we have FO and L. That's good. So I told you how to do A and B. For C and D, you could do it yourself, or for complete literal answer, please follow the link in the description. If you want more of this, please subscribe and tell your friends. Okay, bye.